Welcome to Learning Python, and in this episode we're going to learn how to make an AI model that is able to recognize handwritten digits in the Python programming language. So before I get into anything here, I just want to tell you guys this tutorial it's going to be pure coding, no conceptuals about the neural networks or how it's trained, and let's get right into it. So as you can see, I'm in Google Colab today, not Visual Studio. And what's so great about Google Colab is it's free, first of all, it doesn't require a download, you just need to download a browser. And most importantly, you can connect to a GPU. Now, a GPU is something called a graphical processing unit, and essentially they're used for crunching a bunch of numbers, which are really useful for neural networks. So you're able to connect one even if you don't even have a GPU with you. And second of all, this is a Python notebook, which are really useful for machine learning because you're able to run certain parts of code to be able to experiment. So first of all, to get to Google Colab, you just need a Google account and Google Chrome. So just create a new tab, type in colab.google.com. You'll be redirected here. And in this little window, you can create a new notebook. You'll be taken over here. You can rename your file. Just remember to keep that little suffix IPYNB there. And we can get right into it. So our first step to creating this model is to import dependencies. And the library we're going to use today to create our model is something called PyTorch. And I'm just going to go a new tab right here and type in PyTorch. So PyTorch is a library that people use to make these AI models, and it's really useful, it's versatile. It's personally my favorite. However, there are a few other options that you can use. So if you want to learn more about PyTorch, there are docs that you could learn, there's tutorials, a lot more. Let's get started. Our first thing we need to import is Torch, short for PyTorch, and we're also going to need to import Torch Vision, which is a subset of PyTorch, which is used mainly for computer vision. And from Torch, we're going to import NN and Optim. And these are two libraries. NN is used for making neural networks. Optim is short for optimization, which is where you train and optimize your model. And also from torch.utils.data, we're going to import a data loader. This data loader is essentially something that we use to load in data into our model when we're training. And from Torch Vision, we're going to import datasets and transforms. The datasets is the subset, where all the datasets are stored, and transforms is a library that we use to, augment and change our data to get it ready to be inputted into a model. So we're gonna run that. Let's hope there are no errors. So now that this is done, importing, I can finally tell you guys how do we connect to a GPU. So to connect to a GPU, you can go to this runtime tab and click on it and go down to change runtime type, and you can click on T for GPU. So what I'm gonna do is I'm gonna click on it, but here's the thing. It's gonna disconnect and delete your runtime, and also you're given a time limit because this stuff is free and there are a lot of people using it. So I'm actually not gonna use it just yet. I'm gonna stay on my CPU. Once we're done coding, we can finally connect to a GPU, and then we can run everything. So I'm gonna create a new code cell, and we can finally get started. So I'm going to create a variable called train. I'm going to set it equal to datasets.mnist. So mnist is the name of a dataset that's stored inside this library, and it contains around 70,000 images of handwritten digits. It's a great model to start out with if you're just starting computer vision. So this needs a few parameters. We're going to need a root, which we're going to set to data. And we'll also need a train. We set that to true. We also want to download it. Let's set that equal to true. And there's also going to be a transform. We'll put that in later. And let's do the same for test. I'm just going to copy this, paste it down there. Let's rename it to test. And then so a transform is essentially how do we change this data so the computer can understand it. So in its raw form, the MNIST dataset are images, but computers understand through numbers. So we're going to need to create a transform that converts these images to numbers. So our transform, we're going to create a variable here that equal to transforms.compose, and then we're going to type in transforms.toTensor. So a tensor is the data type that all PyTorch models use, and essentially all this does is it converts our data into numbers. And we're just going to go down here, type in transform here. Transform. Now let's hope this runs without any errors. You can see it's downloading. Let's let that finish. So it's all done now, and we can open up our file here. And you can see we have data. That's because we specified the root. We can click on a drop down here. And you can see we have a bunch of data packets here, which all our images are stored in. So now we can create some data loaders. This is essentially how we load in our data into our model. We're not going to use these just yet. We're going to use them in the final step, which is where we actually train our model. So train data loader, we're going to set that equal to data loader. And our data set is going to be the train data set and our batch size. So I'm not really going to get into it too much. It's just that, AI models like taking in data in batches. So this data loader will essentially batch up our data into various pieces. So we're going to set the batch size into 32 images per batch. We're going to shuffle our data, and that should be it. We're going to copy this, put it down here, and rename our data loader to test data loader. The data set to test, and then that shuffle to false. Run that. Works perfectly fine. And now I think we can get into some more exciting stuff. We can finally start exploring our data. So before we start exploring our data, I'm going to import two things. I'm going to import random, and I'm going to import matplotlib.pyplot as PLT. So the thing about our trained variable right here, or we can do our test. I'm going to do train in this scenario. So the cool thing about our train is that we can actually index certain data points. So 60,000, we can import, let's just say the fifth one. And what it is, we have our image here converted into number form, and also we have a tuple. So it's an entire tuple. We have our image and actually what it is. So this image is a 2, as you can see right here, and then everything above it is actually the image. And if we index it to its first one, it's just going to be just the image. So there's actually a way that we can actually view this image, and the way we do that is through matplotlib. What we'll do is plt.imshow. And then this is actually going to return an error if you run it just here. I'm going to do .squeeze. And I don't really want to get into it. It's just about the shape of our tensors and the way that matplotlib processes. So I'm going to run it. And you can see that it's a 2. And actually, if you want it to be, black and white, we can just press a comma, cmap is equal to gray. You can see that works. Now, if you want to get, a random image, we can do random.randint. Like a range from 0 to 100. You can see, we get a random image. Let's try running it again. Accidentally put in a comma. Rotation. You can run it again. You can see we have 1, 3, 1 again, 0. As you can see, that's how we can visualize our data. And I think we can finally move on to creating our model. Okay, so now we can finally get into creating our model. So, first of all, let's type in class, net, and into parentheses, type in nn.module. And then after that, we're going to type in def init self, and we're going to pass in one parameter. We'll call it fc input features, and then super dot init. So now we can finally get into creating the architecture for our model. So we're going to use something called convolutional neural networks, and a short way to say it is CNNs. And essentially these are types of neural networks that are really efficient for using computer vision, and essentially everyone uses it when you're using something related with images. So our model is going to be split into two parts. Our first part is going to be the convolutional part, and essentially that's going to extract patterns that the computer can find, and the last part, it'll convert these patterns that it found into some predictions. So first we're going to type in self.conv, short for convolutional. We'll set it equal to nn.sequential. And essentially what this does is it binds a bunch of layers together. So first we're going to need nn.conv2d in channels is equal to 1, out channels is equal to 16, kernel size set it equal to 3, 3. And then there I'm going to put nn.relu. And what this does, it just takes negative inputs, sets them to 0, and then positive outputs keeps it the same. After that, I'm going to put something new. It's called nn.maxpool2d. Kernel size is equal to 2, 2. Now all this does is it scales down our image. Now you may be wondering, why would you do that? We lose some of the patterns that are in this image. And we just do it for performance purposes because it actually doesn't change, how much the model is actually recognizing. And then finally, I'm going to take everything we have up here and I'm just going to paste it down here and then fix the indents. There we go. And then we're going to match the channels together, 16, and we'll put this like 8. And that should be it for our convolutional part. If there are any errors, we can just go back and fix it. Let's move on to our, our recognizing part, where it converts these patterns into predictions. So self.fc1, short for fully connected layer. I'll just call it FC actually, and then is equal to nn.sequential. And then first thing is nn.flatten. Because the data before is in a 2D format, we want to convert it to a 1D format. And then finally, nn.linear in features is equal to, we'll set it to our FC input features, and our out features is going to be 10 because there are 10 possible numbers that this thing can recognize. All right, so that should be it for our architecture. Now let's put in a function which will, pass our data through it. So def forward, and you really want to name this forward. You don't want to name it anything else. Just remember that. And then self, and then x. X is going to be our data, and then we're going to return. The first thing we do is you pass x through conv, so self.conv x, and then finally we pass it through self.fc. That should be our architecture for our model. So our next thing that we want to do is let's finally initiate our model. So model is equal to net. And then our FC input features, I'm just going to set it to 1. Finally, now if we type in model and print, we finally have a nice little thing right here. So let's try passing some data through this. So I'm going to put parentheses, and I'm going to do torch.rand 1, 1, 28, 28. And this is, rand is just, it gives you just a random tensor and it gives you a shape. So we're going to pass it. You can see we actually have an error here. That's because we defaulted this to 1. We actually want it to be 968. So let's go up here to 968. Nope, we gotta remove that. Yeah, there we go. Let's try passing it. You can see we finally get some predictions. And now the final thing we want to do for creating our model is we want to make this thing device agnostic. Because here's the thing, Torch works differently when it's on a GPU than on a CPU. What we do, first thing we want to do is we want to find our device. So we'll find our device, we'll set it equal to CUDA. CUDA is the software that Torch uses when connecting to a GPU. Is device equal to CUDA if torch.cuda.is_available else CPU. And right now our device should be CPU because we haven't connected to GPU yet. And then what I'm going to do, I'm going to move this little device code up 1. And then what I want to do is I want to port this model to our device. So it doesn't matter if it's a CPU or a GPU, our model will be on the correct type of hardware. Okay, so now that we have that done, we can finally move on to the next step, which is where we finally start training our model. All right, so we're almost there. The last thing we need to do is train our model. So the first thing I'm going to do is we're going to create loss and optimizer functions. So our loss function is a function that calculates how good or bad our model is doing, and our optimizer function optimizes and trains our function. So our loss function, I'm going to call it loss fn. Some people call it criterion, but I like to call it loss fn. And I'm going to set it equal to nn.cross entropy loss. And then our optimizer, I'll set it equal to optim, which is the function, not the function, the library that we imported all the way back. And we'll use atom. Now atom, it's just a type of optimizer. I like to use it for multi-class imaging, multi-class computer vision problems. So our params are going to be model.parameters. And that should be it, besides learning rate, which is how much our model's parameters get changed. And I think we should be good for that. Let's press enter, and we should be good for that. Now we can finally move on to our training loop, which is where our function actually learns from the data set. So first, we're going to need to use a variable here. We'll set equal to 5 epochs. So essentially, this is going to be how many iterations our model is going to train off of the data set. So we're going to create a for loop for epoch, in range epochs. And then I'm going to create two variables, train loss, test loss. And I'm going to set them both to 0. This is going to gauge how well our model is doing on both of the data sets. And next, we're going to finally get into training our model. So for batch, this is going to be whatever batch we're on. And then XY, X is going to be our images and Y is going to be our label. And then it's going to be in enumerate train data loader. Next, we're going to make our data device agnostic, which means it'll be able to work on CPU and GPU. So x.toDevice, y.toDevice. There we go. And now we can do a forward pass, where we pass our x values, which is x right here, into our model. So we'll call it y hat, and we'll set it equal to model x. And then our loss fn, can be our y hats and our y. So essentially our loss function is going to compare our model's predictions to the actual correct answers, and it's going to gauge how bad or how good it's doing. And after that, we're going to do something called optimizer.0grad. So the way that optimizers work is they use something called gradient descent, and every single time you do a training loop, then you want to zero out the gradients, because there's something called gradient accumulation, which really isn't good. Just remember to zero grad. So optimizer.0grad, and then we do loss.backward. And this is something called backwards propagation. It assists in training. And then finally, optimizer.step. And what this actually does is it'll update all the parameters for our model. So that's all it's going to be for training. Let's move on to our test loop. So first of all, I'm going to type in with torch.inference mode. And inference mode is a mode that turns on and improves performance. And then we'll do for batch, just the usual XY, in enumerate test data loader. Test data loader. I apologize for my bad typing. And then we'll convert it to device agnostic code. y.toDevice. Finally, we'll get our y hat. We'll set it equal to model x, and then our loss, we'll set it equal to loss fn, y hat y. That's going to be it for our testing right here. And now we're going to finally put these two variables to test. So every single time we do an iteration, I'm going to go up here. I'm going to add train loss plus equals loss.item. So item just converts it to a Python float. And essentially this will add over time, and at the end, we'll set train loss, and we'll divide it by how many batches there are, so length of train data loader. And after that, we're going to print string train loss, and then we'll put in train loss, and I think I'll round it to we'll do 3 points. 3 points would be good. And we can just do the same for our test loss right here. So test loss plus equals loss.item. And then at the end over here, we're going to do test loss divides equals length of test data loader. And then we'll print the same thing, print string test loss, and then test loss, round it to 3 places. Okay, so I hope this is work. There's always errors because, there's always a place where you can mess up. Let's hope that everything works fine. You can see it's working. Now the problem is that this is going to take a pretty long time. The reason why is because we're on a CPU right now. And what I'm going to do is I'm going to stop this, and we can finally convert to a GPU. We'll do runtime, change runtime type, T for GPU. Now this is going to disconnect and delete our runtime, but let's go down here and click on this code cell, press runtime, run before. So everything before should run, and we can finally get to training. So now that we're done running everything before, we can almost get to training, because I actually found an error that we actually had. So you can see right here in our train loop that we have batch xy in enumerate test data loader. Now I actually forgot to capitalize our x over here. And the reason why this is so important, if you keep it at lowercase x, and I have capital X up here, that means it's taking the data from our train set, which really isn't good because it'll make our test loss, way too inaccurate. So now that that's all good, we can finally get to training. Okay, so now that our model is finally done training, the final part of this video will be evaluating our model. So let's go ahead and create a new code cell. And I'm going to take just one random image from our test set. So random image is equal to random.choice. And it's going to be from our test data set. All right, so now that we have a random image, let's just see what it looks like. Okay, good. So now what we're going to do is we're going to get some data from it. So our random image tensor is going to equal to random image 0. And our random image label is going to equal to random image first one right there. Okay, good. Now that we have that, we can finally start predicting. So the first thing I'm going to do here is I'm going to take our model. Let's see what happens if we try passing a random image tensor. You can see we actually have a device error because our model is on the GPU, but this tensor is actually on the CPU. So I'm just going to go right here, .to device. This is why device agnostic code is really important. And you can see we actually have a matrix error right here. Let's see if we can sort that out. I'm going to try to do a little .unsqueeze. I'll put the dim on 0. Let's see what happens. All right, that's pretty cool. So you can see right here, we have some numbers right here, but what's pretty confusing is that we can't really get much from it. So we actually pass it through a function right here, and it's something called a softmax. And what it does, it takes these things called logits. They're a type of they're called raw predictions. And what it'll do, it'll convert it to these percentages. We'll do torch.softmax. And then our dim, we'll put it at 1. You can see we finally have some predictions. And now let's see what will happen if we do .max. And you can see we finally have one that our model's pretty sure of. And we'll do argmax to get an index here. That's going to be 3. So you can see our model predicted that this number was going to be 3. Let's do plt, which is matplotlib.imshow random image tensor .squeeze, and then cmap is equal to gray. And you can see again we have another device error because matplotlib cannot use GPU. So I think I'll just do .cpu at the end. You can see we have 3. Now let's try doing these for some other images. The random image, let's get a new one. It predicts this one to be 2. And once you look at that. So that's going to be it for this episode. We finally managed to create an AI computer vision model that is able to recognize handwritten digits. I'll see you in the next one. Goodbye.